So Dr. Sagar, you have 20 minutes of time. So when it's about 18th minute, I will just remind you. Kindly share your full screen. So I will stop sharing now. So over to you, Dr. Sagar. Please go ahead.
Yeah. Am I audible?
Yes, sir.
Yeah. Uh, Thank you for your kind introduction, and I apologize for the delay. There were some technical difficulties from my laptop, so I have switched to my colleague's laptop. Anyway, good afternoon, everyone. Today, I'd like to talk about the thing which have been done from our group using ADF program package in the last few years. So in the early days, computers programs were getting developed, it was able to generate a lot of numbers. So there were complaints from the community, especially Coulson. He said that give us insight, not the numbers. However, over the years, the field is matured now. The current view is give us insight with numbers. There are so many software packages available for doing routine computational stuffs like optimization, frequency calculation, or transition state location. However, ADF had a very unique facility, that is energy decomposition analysis, which gives an opportunity to give more insight into the chemical problem, especially the bonding. So in this in energy decomposition analysis, it decomposes the energy into four terms, that is electrostatic Pauli, called static term, and orbital interaction terms, which character, and the third term, that is a dispersion term. Along with the energy decomposition, it has another unique facilities, that is energy EDA NOCV analysis, which gives beautiful pictures from where we can give chemical insights, and it gives the deformation density associated with this pairwise orbital interactions where the charge flow is from red to blue. So broadly, chemical bonds can be classified into three categories, that is covalent bond, ionic bond, and metallic bond. And covalent bond could be further decomposed into two major categories, that is electron shared bond or dative bond. And organic and organometallic chemistry mainly are dominated by this covalent bond, where the orbital interaction terms from the energy decomposition analysis gives much insight into the this part of the chemistry. So this is my plan of the talk. At first part, I would discuss about the nature of the chemical bonds, and where I would try to build up this donor acceptor bonding model using energy decomposition analysis tool, which is there in ADF. And in the second part of the talk, I would discuss about the non-covalent interaction in different domains, where since non-covalent interaction is mainly dominated by the electrostatic interaction, so I have put it in under the category of sterics. So we'll discuss two of the terms, like orbital interaction terms and the steric terms, and finally I would summarize my talk. So I start with this boron-centered lone pair. So as we all know, boron has 3 valence electrons. So in tri-coordinate boron, it generally used to be electron deficient. However, it was shown that by proper ligand environment, we can achieve a lone pair on the boron centers. But in order to understand the electronic structure, it is absolutely necessary to select the most favorable fragment. One could at the very first start with the ground state electronic configuration of the two fragments. This is a schematic diagram. Let's say this is fragment 1, this is fragment 2. And in this molecule, I can have BF as a fragment 1 and the rest of the two ligands as fragment 2. Now, the first obvious choice is we start with the ground state electronic configuration and determine the orbital interaction energy. However, that may not be the most favorable fragment in that molecule. We then need to first check the orbital interaction considering different excited state electronic configuration as well. And if the excited state electronic configuration interaction is lower than the ground state one, so we consider those as the most favorable fragment. And this can be done with frag occupations keyword. So one can play with the frag occupation keyword to have different electronic configurations for different fragment. So this is a sample input for this to perform different excitations in this molecule. So finally, one select the favorable fragment and do the analysis. So in this case, this is a EDA-NOCP analysis for this molecule. You can see here the red region corresponds to electron-rich region, and this blue region corresponds to electron-deficient region. So there is a charge transfer from the red region to blue region, which I have put it schematically like this, which we call it as a back donations. And in addition, there are two other important orbitals which can be seen from EDA-NOCP analysis. And if I put it into a schematic diagram, which are nothing but the ligand stabilizing the boron vacant orbital, that is this sp hybrid orbital and p orbital through these donations. So as a result, this ligand donations and back donation is operative to for stability of this molecule. Therefore, EDA-NOCP analysis, which is there in the EDA, is a very useful tool to give a electronic structure analysis for this molecule. Not only that, with the help of this donor acceptor bonding model, we can also predict a new molecule. That is, here we have shown the design of BB triple bond in a cyclic system. So we know that if a carbon, we have sp hybrid orbital that would have 180-degree angle. However, if we want to make it in a part of a ring, then there will be angle strain, which would not allow it to form the cyclic triple bond system. However, metal finds a unique way to stabilize this, and it was shown in 2002 for the carbon metal cycles. However, we wanted to see this boron-boron triple bond, linear triple bond is known from 2012. We wanted to see, can we have this similar BB triple bond in a cyclic system? One obvious choice, one can go from carbon to boron. However, that would make it a efficient system. So electron sufficiency can be made by changing the end carbon by 2 nitrogen. Therefore, it would be an electron sufficient system. However, this electronegative perturbation would change the electronic structure dramatically. And the electronic structure analysis was done using the fragment molecular orbital analysis, which is there in the ADA program package also. So here we have decomposed the molecule conceptually into two fragments, like ZrCp2 metal fragment and the rest N2B2 fragment like this. And as I have already mentioned, boron is a 2 electron deficient system, so the pi orbital is not occupied here. However, that pi orbital is getting filled up from the metal 2 electrons like this orbital. So in a molecule, this pi orbital is receiving electron from metal center. And there are two other important molecular orbitals, this one, which are mainly localized on the nitrogen center. So that can be also shared as a nitrogen center lone pair, giving stability to the metal vacant side, and other electron to plane pi orbital. So it's again donor acceptor bonding model, which is explaining the electronic structure for this molecule. And also one can see from the EDA-NOCP analysis that there is a charge donation from the metal to the in-plane pi orbital of boron, that is Zr2b2 donations, and nitrogen centered lone pair is giving stability to the metal vacant side. So, and also we have shown a difference contrast between the carbon and boron, where carbon prefers the electron sharing bonding, as you can see here. However, boron prefers another kind of covalent bond, that is donor acceptor bonding. So it is useful to distinguish two kind of covalent bond, and EDA-NOCP analysis is a very useful tools to show the distinction between these two bonding pictures. So not only that, not only for the standard bond with excess isocyanide gives 3 products, where the first product, that is complex 2, which is a singlet product, where it is a septate product. The spin multiplicity is septate. However, a controlled reaction was performed where treatment of complex 1, leads to another spin state product, that is complex 5. So as a whole, we have 3 spin state involved in this reaction. Singlet, my starting point is singlet, however the products are singlet, quintet and septet. So there are different spin multiplicities involved in the reaction. But in contrast, when the reaction was performed with carbon monoxide, which is a valence isomer of isocyanate, it gives only one product, which is a singlet product. So we have shown the detailed mechanism in this paper. I will not go into the details, but what I would like to highlight here, that how EDA NOCB analysis helped us to pinpoint where what distinguishes this carbon monoxide with isocyanate. So this intermediate one was a very crucial point from where there was a spin state crossing. So energetic shows that in the case of isocyanate, singlet state higher in energy, however there are quintet state which is lower in energy. So energetic shows why there would be a spin state crossing for isocyanate. However, for carbon monoxide case, singlet state was the most stable state, so it did not undergo spin state crossing. So the color code for isocyanide is blue, and for carbon monoxide, which is oxygen, X is oxygen, that is red. So in order to understand what is the difference between this isocyanide and carbon monoxide, we have decomposed this molecule into 2 interacting fragments. One is the CX fragment, which is either isocyanide or carbon monoxide, and the rest of the fragment. And then we found that the orbital interaction energy term is much more for carbon monoxide and compared to the isocyanate. In fact, this EDA NOCV, this ADF gives another opportunity to measure also separately sigma donation and pi back donation. This ligands has synergistic sigma donation as well as pi back donation capability, and we found that sigma donation capabilities are same for carbon monoxide and isocyanate. However, pi back donation is very strong for carbon monoxide. So, which distinguishes the nature of carbon monoxide with respect to isocyanate. And this CSOV analysis allowed us to show that this removal of the electron count from cloud from the chromium-chromium bonding region was the principal reason for the distinction between these 2 reaction channels. And yeah, so EDA NOCB was again helpful to give insight into this problem. So let me move into the second part of my talk, that which involves the non-covalent interactions. So group 6 transition metals like chromium, which has 6 valence electrons. So when they form dimer, it has a possibility to give highest bond order possible for a transition metal, that is 6, which are 2 sigma, 2 pi and 2 delta, which a molecular orbital diagram is shown here. So we have 2 sigma, 2 delta and 2 pi, and the corresponding MOs are here. However, one interesting feature for this molecule is that the bond dissociation energy, even though the bond order is 6, the bond dissociation energy is even smaller than the single bond, that is only 35 kilocalorie per mole. And also another interesting experiment was there, where the electronic excitation from the singlet to triplet state did not change the energetics. So which indirectly shows that there is a tremendous electron congestion at the internuclear between the 2 nuclei, and which was due to this effect. So when so this is a plot where orbital overlap was measured by varying the chromium-chromium distance, and this vertical line corresponds to the equilibrium distance, and this black curve corresponds to the orbital overlap change due to sigma bond formations, and this red corresponds to delta, and this blue corresponds to pi bond formation. As you can see that sigma bond, the maximum overlap was in the higher bond distance region compared to at the equilibrium distance. However, this delta and pi bond, the maximum overlap could be even possible even if you bring to nuclei closer. So it is the sigma bond which was the main reason for the electronic congestions. So this sigma bond is the responsible factor for electronic congestion. So now we see that sigma bond was the reason for the electronic congestion. Can it be possible to extract out that extra electron density from this? And we showed that yes, by help of the halogen bond formation, we can extract out the extra electron density on the at the internuclear distance, because the sigma hole sitting at this position, which is very directional. So it is possible to extract out the only sigma electron density without touching the pi and delta framework. Indeed, computation shows that after the complexation, there is change in the bond distances, means the bond distance decreased, and which is again reflected from the increase in the vibrational frequency, and also which leads to increase in the interaction energy between the two metal centers from 3 to 3.58 kilocalorie per mole, and which is same for the molybdenum case. However, for tungsten case, there was a reversal because of the relativistic effect, so which I'm not going to talk about here. So what I want to show here is that again energy decomposition analysis helped us to pinpoint what are the responsible factor for this thing. So after the complexation, we can see that there is a decrease in the Pauli repulsion. That is because we are extracting the sigma electron density, which was congested at the internuclear distance. At the same time, electrostatic uh, also destabilized a certain extent, and as you combine, this effect was like this is a destabilizing effect, because we are dividing the molecule here, not the here. However, there is a very much increase in the orbital interactions term, and as I have already showed that there will be gain in the sigma as well as pi and delta term, which can be seen after the complexation. There is a net gain of the sigma stabilization as well as pi stabilization and delta stabilization, and combiningly it gives a total stabilizations of the bond, and which can be repeated for the molybdenum systems also. And tungsten, there was a reversal because of the relativistic effect. Let me move on to the last part of the talk, where I want to highlight another interesting feature which was found from the covalent non-covalent interactions here. So Z bonds, which are there for the almost all of the main group elements. When Z is hydrogen, this is a special case like hydrogen bond. However, there are all kinds of bond reported in the literature considering elements across the periodic table. However, we did not find any example involving this transition metal system. So we wanted to find out the reason for what is the reason not to have the metal bond for transition metals. And indeed, we EDA NOCB analysis quickly led us to check what are the available examples there in the literature. This is a Cambridge Crystal Structural Database search was performed by looking at the electron probe, and which led us to categorize two kinds of bond, that is halogen bond versus metal bond. And we found that the type 2 complexes are having indeed metal bond, where we have metal with field d orbital, and we know that field d orbital behave like main group, so which is not a special case, but we wanted to find out the reason why type 1 had a reluctance towards metal bond formations. And indeed, we found that primogenic repulsion is the responsible factor, that is like the valence orbital 3d orbital, which should be the responsible for that metal bond which lies inside the core orbital, that is 3p orbital or 3s orbital. As a consequence, what will happen is that when a ligand will come, there will be tremendous repulsion between the incoming electron density and the core electron density, and that was the reason there was no metal bond for this partially filled metals. So I would like to say the highlight of this paper here, that in case of main group, we have a sigma hole accessible to form a Z bond, and for the filled orbitals also sigma hole was accessible. However, for partially filled metal D, there was this sigma hole was inside the core electron density. Therefore, it has a repulsion at this position. Therefore, it was not having the metal bond. However, designing an extreme ligand environment could make it could lead it to the metal bond formations. And indeed, we from the energy decomposition analysis, we showed that electrostatic is the main responsible factor for this metal bond, which is a general phenomena for Z bond. So this leads to summarize my talk. I think I could convince you that indeed energy decomposition analysis, which is there in the ADA program package, is a very useful tool to give insight with valid numbers. And in the first part of the talk, I have shown how orbital interaction terms can give insight into already existing molecule electronic structure description, and also allow us to predict new molecule and also give insight into the complicated reaction, and also design some new molecules and also find out the reason why there is a reluctance for a M bond formation. So as a whole, I would say that the success of any computational program or software is that it should be able to give insight into the existing problem, and in addition it should be able to predict new molecule, and this exactly can be done by using EDA NSAB analysis, which is there in the ADA program. With that, let me thank you all for listening. Thank you.
Yeah, thank you, Dr. Sagar, for your wonderful session. So I'm
Yeah.
sure that participants will have a few queries now. So I request everyone to unmute yourself one by one to ask questions, and after that we will take the questions by chat. And there's one more request. I want everyone to mute yourself. Only whoever want to ask the question, they can unmute themselves. And even Dr. Sagar, you also can mute yourself. So you can unmute when you want to answer those questions.
Okay.
Okay. So yeah, you can go ahead with the questions if you have any questions.
Hello.
Mr.
Good evening to all.
Yeah.
Good evening, sir. Sir, can you please go to slide number 24, where you shown the bonding between the two metals, the chromium and molybdenum and tungsten. Just
I request
just a
everyone to
slide,
mute yourself.
the next slide. Hello.
Yes, can you repeat your question once more? Hello. Hello.
Hello. Am I audible?
Yes, yes.
Yes,
Can you
sir, you're
repeat?
audible.
Okay.
You can go ahead.
Okay. Can you go just a slide ahead? The next slide. Where
Yeah.
you have shown the tungsten bonding with itself, tungsten 2. Okay, so yeah, this one. So
Yeah.
I just wanted to ask that here you said that the chelation did not help in the case of tungsten because of the relativistic effects. Can you please elaborate that thing?
Well, uh, okay. So there are actually other factors also along with the relativistic effect. So as I have already mentioned here, the primogenic effect in the next slide also. So due to the primogenic effect also, there will be a hybridization of the d and s orbital for the tungsten, which will allow it to not have repulsion at the sigma bonded region, in contrast with the chromium and molybdenum case. So it's actually this 5D element is sometimes behaves quite different compared to the 3D and 4D because of
So it.
many factors. One is relativistic effect, another would be the hybridizations with primogenic
Okay.
effect also. Yes.
Okay, so like due to the contraction of the s orbitals and expansion of the d orbitals,
Yes,
so they
yes,
are
yes.
getting
There will be
hybridized.
hybridization. Yes, yes.
Okay,
ST
and sir,
hybridization would be there
uh,
in. This is you can find out in this paper also
mhm,
for more elaborate explanation. But more or
mhm.
less the answer would be that.
Okay. Okay, sir. Thanks a lot.
Yeah.
That's it from my side.
Participants can go ahead with their questions if you have any questions to Dr. Sagar.
Hello, sir. My name is Musawir Pasha. Sir, just I wanted to know that how to set up these the how to set up for the calculation of electron transfer between the metal to metal centers, sir. Like in our biferrocene molecules, like thus, how to set up the file, input file.
Okay. Yeah, I will give a bit, concept here. Like if you want to see the charge transfer between two fragments, so first thing one has to do the select the fragments. So once you the fragment, then you can set up your calculations based on what you want to do. So like in my case, I wanted to just uh, see the electronic structure of the interactions of BF fragment with the rest of the fragment. So maybe in your molecule, you want to see one metal fragment with another metal fragment. So you just divide it into two fragments. Like here I have BF fragment and fragment 2. So this is a special features in ADF which allows me to play with the electronics like excitations of the electrons to the higher excited state. However, for your case, you would be seeing only the ground state interactions. Maybe that would be just easy. You just define the two fragments and then see the charge flow, which can be easily done. Maybe in the hands-on session, they would show. But the basic idea is like define your fragments and set up the calculations.
Okay, sir. Thank you.
Yeah, welcome.
Excuse me, sir. Hello.
Yes, I can hear you.
Yeah, yeah. I have one more question. Sir, I wanted
Yeah.
to know that how do we actually incorporate relativistic effects in this model
Oh,
in ADF?
that ADF GUI gives, yeah, ADF GUI gives a option. You just click, turn on
Mm-hmm.
the relativistic keyword.
Mm-hmm.
Like there are different ways to just
Okay.
turn on that. Maybe you can.
Okay.
And for I
Okay.
think heavier
And
metals,
mhm.
yeah, for heavier metals, I think it's a default that it already takes a relativistic effect. But you can always turn it on and off.
Okay, so there is one more question that is there any study on gold, because I know that gold has shows the maximum relativistic effects among late transition metals. So are there studies based on
Yeah,
gold, similar studies which you had done?
it should be there because gold is very famous for that. I'm not
Okay,
sure. I don't have specific reference now.
okay, okay, sure, sure. Thanks a lot, sir.
You're welcome.
Sir, I'm Dr. Rima Vishwas. I have some question. Sir, can I calculate the thermodynamical properties? Like if I want to calculate the free energy, that is Gibbs free energy or the enthalpy. So can I calculate it?
Hello.
Yeah, am I
Yeah.
audible?
So
Yeah, yeah. Yes,
yes,
sir.
yes, yes, yes. So it gives actually for thermodynamic property, you need to do the like frequency calculations and which gives the energy values.
Yes.
So today's presentation, I have mostly shown the energy decomposition analysis, not focused on the thermodynamic, but it can be done. You do the optimization and frequency calculations, and from there one finds the thermal contributions from the energy values, how the thermal contributions are there. It is possible. But in my presentation, I did not. Probably tomorrow there would be reaction mechanistic study details. So in that presentation, it will be there.
Okay, sir. Thank you.
Yeah, welcome.
Is there any other questions? So due to interest of the time, we will take other questions via Discord, which we have already emailed the links, and once again we will put it in the chat section. So Dr. Sagar, thank you very much for your wonderful session.
Welcome, Nina.
So our second speaker of the day is Mr. Sayan Datta. I hope Mr. Sayan Datta is with us, and welcome to the session.
Yes, I can hear you.
Yes, sir. Thanks for being this part of the session. So, Dr. Sayan Datta will be focusing on flourishing chemistry of carbon stabilized main group compounds for insights for theory. So, Dr. Sayan Datta is a senior research fellow in the group of Professor Debasis Kohli at IISER Kolkata. So, he obtained BSc Chemistry from Visva Bharati University in 2011. Subsequently obtained his MSc Chemistry in 2013. So pursuing PhD under the supervision of Professor Debasis Kohli in the Department of Chemical Sciences at IISER Kolkata. So his current researches are on mechanist investigation of main group and transition metal mediated chemical transformations and exploration of the bonding scenario in various donor acceptor complexes employing state of the art computational methods.
The title of my presentation is The Flourishing Chemistry of Carbon Stabilized Main Group Compounds Insights from Theory. So I'll show three of our recent works that is portraying the stabilization of main group compounds utilizing carbons. Before going to my presentation, I will briefly explain energy decomposition analysis, which decomposes the interaction energy between two fragments A and B in a molecule AB into three physically meaningful terms. That is quasi-classical electrostatic interaction between the Fougeant charge densities of the fragments, Pauli repulsion between the occupied orbitals of the fragments, and orbital interaction between the occupied and unoccupied orbitals of the two interacting fragments. And the recent approach in NSU approach by Mithodaj and Michalak also partitions the orbital interaction into the contribution of the orbitals belonging to different irreducible representation and provides us the paired orbital interactions. The first one is bonding investigations of carbon phosphonates, correlation between 31B chemical shifts and bonding features to estimate the pi back donation of carbons. The carbons are generally divalent carbon with a pair of non-bonding electrons and therefore capable of exhibiting singlet or triplet ground electron state. The recent use of carbons in the field of catalysis has interested the research community in estimating the sigma donation and pi back donation of carbons. There are various techniques reported in the literature that can be used for the estimation of donor properties of carbons. That is Tolman electronic parameter, and ligand electronic parameter, calorimetric measurements, and evaluation of 13C NMR chemical shifts in various palladium complexes containing carbons. These methods are excellent in estimating the donor abilities of carbon. However, they fail to estimate the sigma donation and pi back donation of carbons individually. Barton et al. Recently reported the convenient method to estimate the pi back donation of carbons by utilizing the 31P NMR spectroscopy of the carbon phenyl phosphonating adducts. So in the present study, we have explored the bonding scenario in carbon phosphonating adducts using various computational tools. Carbon phosphonated adducts mainly exhibits three resonance forms. Form X correspond a typical phosphoalkane with a carbon phosphorus double bond and a lone pair at the phosphorus, whereas the other two resonance forms Y and Z actually shows the donor set of carbon phosphorus bonds, and the stronger sigma donation from the carbon carbon makes the phosphorus electron rich compared to that in X. So I have schematically presented the bonding features in these structurally attractive compounds. So for this study, we have considered 21 different carbons of diverse electronic and steric nature. So we have calculated the 31p chemical shifts in these carbon phosphonated adducts. Our calculation shows that the NEC carbons show significant significant upfill shift compared to the celiac and recently reported bica carbons. And the carbon phosphorus bonds show partial double bond character as indicated by the Weber bond indices values. The sigma polarization to the phosphorus actually are similar across the carbons. On the contrary, the carbon phosphorus pi polarization to the carbon center actually varies with changing the carbons. We have obtained an excellent correlation between the calculated and experimental chemical shifts for both 13C NMR and 31P chemical shifts. So next we have checked the correlation of different bonding parameters of these compounds with the calculated 31P chemical shifts. Our calculation suggests excellent correlation of the between the chemical shifts with the carbon phosphorus pi polarization to the carbon carbon and NP charges on the phosphorus, unlike the sigma polarization to phosphorus. These are the selected molecular orbitals in these compounds. The homos in all the compounds represent carbon phosphorus pi orbitals. So QTM calculations suggest the donor-acceptor nature of the carbon phosphorus bonds in all the compounds and the energy density values, which indicates the covalent contribution to donor-acceptor bond, is obtained maximum for 13, that is the phenyl phosphate adduct of EC carbon. Moreover, we have obtained excellent correlation of the calculated chemical shifts with both electron density and energy densities. Next, we have performed ED calculations considering carbene and phenyl phosphate as the interacting fragments to unfold the nature of chemical bonding in these compounds. Our calculation suggests that the carbon phosphorus bonds have substantially higher orbit covalent nature than the electrostatic interaction, and the preparation energy actually is mainly come from the phenyl phosphate fragment due to its excitation from the triplet ground state to the singlet excited state. Moreover, we have obtained excellent correlation between the interaction energy between the fragments and the calculated chemical shift. Next, I have shown two representative examples of carbon phosphonadiens. That is one of the unsaturated NEC, and the other is the corresponding PC carbene. So the major orbital interaction in the NEC actually shows the charge flow from the carbon lone pair to the vacant p orbital of phosphorus, whereas in the PC carbene adduct, actually we have obtained the major orbital interaction showing the pi back donation from phosphorus to the vacant pi symmetric molecular orbital centered at the carbon carbon. So therefore the contradicting deformation density clause can nicely explain the significantly higher pi setting abilities of EC carbenes compared to its nitrogen analog. So here I have summarized all the correlation that that we have checked with different bonding parameters. So our calculations suggest that the excellent correlation of chemical shifts are obtained with carbon phosphorus pi polarization to the carbon carbon, NPA charges on the phosphorus, and also the electron densities of the carbon phosphorus bonds at the T-1 bond critical points, and also the interaction energies between the interacting fragments. Moreover, the singlet triplet gaps and the homologue energy gaps in the free carbenes have no correlation with the or better to say a very poor correlation with the calculated chemical shifts. Next one is cooperative donor-acceptor interactions in stabilizing carbene boron and carbene alane compounds. So the Lewis acidic nature of group 13 compounds actually renders them to have complexation with strongly nucleophilic energetic carbenes. So these various carbene boron compounds are reported in the literature, and these compounds actually have tremendous applications in diverse fields, including the acting as a hydride donors in ionic reactions, whereas they behave as the hydrogen atom donors in radical reactions. So through the extensively the applications of these carbene boron compounds were explored, but theoretically the bonding scenario in detail actually have been remain unexplored. So we have performed so the bonding scenario in these carbon boron compounds, and also compared the bonding situation with these heavier carbon allen analogs. So for the study, we have considered 12 different carbons and 10 different Lewis acids. So similarly, we have to my first work, I have also performed here the EDA calculations considering carbon and boron as the interacting fragments, and our calculation suggests that the carbon boron bonds have almost equally strong orbital interaction and electrostatic interaction, and the whereas in the carbon allen adducts shows significantly lower interaction energy compared to the carbon boron compounds, and the bonds have expectedly significantly high electrostatic nature than the covalent interaction. I have compared the correlation of the interaction energies with the individual energy terms obtained from the ED analysis, and for the carbon boron compounds, we have obtained very poor correlations, whereas for the carbon allen compounds, all the three energy terms shows excellent correlation with the calculated interaction energies. So this is the trends in interaction energies of the carbon boron trihydride adducts, and from this figure one can frame a relative trend in the intrinsic Lewis specificities of the carbons concerning the boron trihydride as a reference Lewis acid. These are the optimized geometries of selected carbon boron trihydride adducts, and the optimized geometry shows significantly longer boron hydrogen and aluminum hydrogen bonds than that in the free Lewis acid, and the extent of elongation of these boron hydrogen and aluminum hydrogen bonds can be nicely correlated with the calculated interaction energy. Next, we have calculated the molecular electrostatic potential surfaces, and the amount of group charge transfer actually is calculated maximum for the abnormal carbon in abnormal NEC, and it is lower for the bicar carbon, and the MEC surface shows the rate near in the vicinity of boron and aluminium, indicating the substantial charge transfer from the carbon to the boron and allen fragments. Next, I have presented the molecular orbitals of free carbene and free BH3 and compared it with the fragments in the adduct. Our computation suggests that the energy gap between the carbene lone pair and the vacant p orbital of boron actually gets drastically reduced in the adduct there, and it is possible only due to the switching of orbitals from the home minus 1 to the HOMO in the carbene fragment, exhibiting the carbene lone pair orbital. Next, I have presented the pairless orbital interactions in 3p3. The major orbital interaction shows the sigma donation from carbene lone pair to the vacant p orbital of boron. The first minor orbital interaction shows the pi back donation from the boron hydrogen electron density that is enriched in increasing pi p character to the vacant p pi orbital centered on the carbon, and the last and very little but non-negligible interaction comes from the sigma back donation, that is from the sigma bonded electron densities matched over the whole overall molecule to the carbene sp2 hybridized orbital, which was earlier involved in the sigma donation. So these are the schematic representation of all the charge flow existing in this compound. Moreover, we have obtained excellent correlation between the extent of sigma donation with interaction energy. So we have computed the energy stabilization associated with sigma donation and pi back donation, and also the sigma back donation in these adducts. So our calculation suggests the maximum sigma donation is obtained for the 5-membered saturated CA carbons, whereas it is minimum for the NAC carbons with these electron withdrawing substituent bonded to the nitrogen atom. For the carbon allen adducts, the maximum sigma donation is obtained for the abnormal carbon, and least for the 5-membered cyclic diamido carbon. Next, we have checked the abilities of carbines in activating the boron hydrogen bonds in boron triiodide and pinnacle boron. So we have taken one recent example from the literature. The reports came from the group of Barton. They have showed that cat actually forms a classical Lewis acid-base adduct with the boron triiodide, whereas they exhibits the corresponding oxidative addition product in the presence of pinnacle boron. So we have calculated the barriers for the beach bond activation for all the carbons, and our computation suggests that the 5-member cyclic CDF carbon shows the least energy barrier, whereas it is maximum of 10. It is required maximum for the abnormal NAC. Similarly, we have performed the beach bond activation in pinnacle boron for selected carbons, and it is obtained. The least barrier is calculated for 5-member unsaturated SCAC, and maximum is obtained for the 5-member unsaturated NAC. So we have performed distortion induction analysis to cast light on the origin of the barriers. So our calculations suggest that the significantly low barrier for these 6 actually is can be explained by the very low distortion energies of the carbon fragments, and similarly for the highest energy barrier calculated for abnormal NEC can be explained by the significantly high distortion energies of the boron triiodide fragments. Similarly, in the transient state involved in the beach bond activation in pinnacle boron, the maximum the maximum barrier is obtained for 3, and it can be explained by the similar manner by the high distortion energy of the beta fragment. Moreover, we have obtained an excellent correlation between the NPH charges on the hydride that is involved in the transfer from the boron to the carbon center, and also the orbital interaction between the interacting fragments. The last one is the bonding scenarios in abnormal NAC bound silyl and SCM silyl radical ion. Recently, Lee et al. Have reported these NAC bound silyl and SCM silyl radical ion. So these silicon 2 cation or silylium iodine actually has the tremendous potential in the field of catalysis due to its availability of lone pair and also 2 vacant degenerate p orbitals at the silicon center. So we have in collaboration with the experimental group, we have performed the bonding scenario in these 2 compounds. Our preliminary reactive calculation suggests the participation of the carbene in single electron transfer, and also the treat solvent plays the role of the hydrogen atom conveyor for the formation of these 2 compounds. So in the presentation, I have focused on the bonding scenario in these 2 compounds. So our calculation suggests the HOMO in 1 plus suggests the lone pair on the silicon center, whereas in the radical ion, a cation, actually the silicon carbon pi orbital is in conjugation with the nitrogen in the carbon ring framework, whereas the LUMOS represent the pi star of the ligand backbone. So this is the molecular dependency plots in the CX radical ion. So unlike the previously reported carbon stabilized silicon radicals, where most of the electron density is residing on the carbon center, here we have computed a significant spin density at the silicon center. So next we have performed EDA calculation to explore the appropriate description of chemical bonding in this NAC bound silyl. So as we know that it can represent 1A plus can be represented by 2 resonant forms. The first one is the coordinate bond, and whereas in the resonant form it is a classical covalent bond with the positive charge residing at the carbene ring framework. So our calculation suggests that the former resonance form actually exhibits the lower orbital interaction, and therefore this compound can be nicely represented by the coordinate bonding description. Similarly, here also the 2p plus, and this one actually that is represents the most suitable depiction of chemical bonding, and so therefore this compound actually possesses the silicon carbon covalent bond with the unpaired electron is sitting at the carbon carbon center. So as the molecular spin density clause earlier suggested, the significant accumulation of spin density at the silicon center, we have performed NSOB calculations also. So as in the NSOB calculation in this radical arm actually is associated with the charge flow from the carbon to the silicon center, and also the this NEC bound silane, the major orbital interaction actually shows the charge flow from the carbon lone pair to the vacant p orbital of the silicon, whereas the minor contribution shows the charge flow from the pi orbital of the carbon ring framework to the vacant 3p orbital of silicon. Finally, I would like to acknowledge my supervisor, Professor Devashish Kole, and all my current lab mates for their constant support and encouragement. I would like to thank Isaac Okada for the computational facility, CSR, DST, and DFG for the funding, SCM for this providing various computational tools that helps us to explore the bonding and mechanism of various transitional metal and mediated chemical reactions, and Nyro Research India for arranging this webinar. Thank you all.
Mr. Sayan, thank you so much for your wonderful session.
Welcome, madam.
So due to interest of time, we will be taking only one question. So anyone is having a question, you can unmute yourself, and rest of the question we will take via Discord. Mr. Sayan, there's one question in the chat. You want me to read out for you?
Yes, I'm listening to you.
It's how the percentage of each interaction of energy calculation in EDA, calculated in EDA.
Okay, actually, EDA calculations actually one to unfold the nature of bond. Actually, we actually generally the percentage of the attack interactions are calculated by the sum by, let's say we have to calculate the orbital interaction, then the percentage can be calculated by the energy values associated with the orbital interaction by the sum of electrostatic interaction plus orbital interaction. If someone use dispersion factor functional, then another attack interactions actually this accounts for the dispersion interaction gets added to the interaction energy, then another percentage will also come.
Sure. Thank you, Mr. Sayan. So you can stop sharing the screen now. So there's a last question there. The energy profile diagram is plotted using which software?
Oh, the energy profile diagram is plotted in just PowerPoint, and actually it is plotted in Excel, and then actually it is projected on the PowerPoint to put the energy values and all the labeling of the individual intermediates and transistors.
Sure. Thank you so much. So due to interest of time, as I already said, we will take rest of the questions via Discord. So we are going to head to the, so we are heading to the last session. So the last session will be taken by Dr. Ole Carterson. Dr. Ole, hope you're with us.
Everybody.
Hello. So we are happy to have you here. Welcome to the session.
Thank you.
So there is a brief introduction of about Dr. Ole. So he'll be focusing on diffusion of LIC batteries and Monte Carlo. So he's a support scientist at SCM. So Ole modeled the dynamics of photoswitchable molecules, receiving a PhD in 2014 with Professor Artke in Kiel. He then joined SCM as a support scientist. Ole has been working on improving usability, graphical interface, scripting, and implementing new functionality in React-FF. His role is currently more focused on helping existing and potential customers to be successful with their advanced scientific applications. So Dr. Ole, you have 1 hour exactly along with the hands-on session.
All right.
So kindly share your full screen. So over to you, Dr. Ole. You can please go ahead.
All right. Thank you. So I'm sharing my screen now. Does that work?
Yes.
Wonderful. Okay. So good evening, everybody. I understand that it's evening in India. Over here in Amsterdam, it's lunch break, actually.
Dr. Ole, sorry to interrupt. Can you share full screen?
Sure.
Okay.
Hold on. Like this?
Yes, it's visible.
Okay. Sorry. Okay. So yeah, good evening, everybody, and I'm happy to be able to present some of our exciting new workflows from the area of batteries research. And what I had in mind for today's session is a bit less of a scientific talk, but a bit more of a hands-on demonstration. So I have only a couple of slides, and I would like to start off with a brief overview of what I had in mind, what exactly I would like to show to you. And this is basically two example workflows. The first one being the simulation of discharge voltage profiles of a lithium-sulfur battery. So what we're going to do is we're going to set up a sulfur cathode and then simulate the discharge process, which is the lithiation of that sulfur structure by means of a Monte Carlo procedure. And from that, we can extract the discharge, the experimental discharge voltage profiles. And in a second hands-on, I would like to simulate the diffusion coefficients of the lithium ions, so the charge carriers inside that very sulfur cathode. So the mobility, as you will. Of course, that's an important measure in this area of research. And the calculations, I think both of them are lasting about an hour or so. So I will go through almost the complete setup. We can start the calculation, so you can tap along if you have an AMS installation. But then I will jump to the result of the calculation at some point. But no worries, if you missed that bit, there's full documentation available online, so you can either click on the links in the slides, which I believe will be shared with you, but they're also accessible from inside the code, as I will show in a second. So, and as for all the exciting science behind this, I mentioned I will give you a brief outline of this, of the approach, just so that you know the basics of what we're going to do. But the hard science can be found in this absolutely wonderful publication on the top here. So if you are interested in batteries research and reactive force fields, React-FF in particular, then that is a brilliant read, I think. Okay, now let's have a look at the first hands-on session and just get an idea of the workflow that we are going to put into action now. So what I will be showing you is how to calculate the chemical potential of the lithium in this system. And in the model assumption that we put in is that the chemical potential of the lithium corresponds to the total energy of a single lithium atom within body-centered cubic lithium bulk structure. So that's the energy that we need to, that one lithium atom inside this bulk structure has. So we can just calculate that with React-FF, and I'm going to show you how that is done. With that chemical potential, we can then set up what is called a grand canonical Monte Carlo simulation. So we will sample a grand canonical ensemble, or trying to achieve a grand canonical ensemble. And in a nutshell, what the algorithm does is it will either try to insert a lithium atom into the sulfur structure, or it will try to remove a lithium atom from the sulfur structure, or it will move a lithium atom around inside the structure, so a lithium atom that has previously been inserted, or it will shrink or expand the volume. So these lithium sulfur batteries have the tendency to significantly increase in volume when they discharge, and this is something that we will also see in our simulation. And the ensemble is reached, say the equilibrium is reached of the grand canonical ensemble when the lithium X sulfur structure, so the lithiated sulfur cathode and the bulk lithium structure are in their thermodynamic equilibrium. So that's also why we needed the chemical potential of the lithium in the first hand. And once we have finished this calculation, and as I mentioned, I will just do a jump forward. The whole thing takes around an hour on a conventional laptop. So I have a 2-core machine here with i7 processors in it, nothing fancy. Takes around an hour to finish. Once it finishes, we can then use a post-processing step to extract the voltage profiles from all the snapshots of the Monte Carlo procedure. Okay, so let's jump right in. I'm going to start by opening a fresh AMS input window. I'm using the latest release, AMS 2021-102. I'm not sure if that is the version that everybody else has. If not, 2020 will work in exactly the same way. Okay, so the first thing I'm going to do is I'm going to click on the help function up here and will open the offline documentation. As you can see, this documentation now is offline. That's lying on my hard drive, and it comes with your AMS installation. So you can use it without having an active internet connection. And another advantage is that it will automatically open the documentation of the version that you have installed. So even if you have 2020, the online documentation might be 2021. If you open the offline documentation, you'll get the right one. Okay, so on the left, there's an overview of tutorials, and we're going to jump right into molecular dynamics and Monte Carlo. And from the overview, we select battery discharge voltage profiles. So this is the whole tutorial. Click resolved. So every single step explained. We don't go through all of this. Instead, I will just go through the tutorial. And if you get lost, then you can always read up over here. And the first thing that I would like to do is actually download a crystal structure of the sulfur structure. So I'm just going to do right click. I'm sorry that my language code here on this computer is in Dutch, so I'm just save as is what I do. It says S8 alpha. And then I can just import this structure by going to File, Import Coordinates into the graphical user interface. It should be on the desktop. There it is. And then we'll wait a second and we can see the structure being imported. So this is bulk structure, which we can easily verify by clicking on the periodic view button here. You can see the unit cell repeated. Switch that off for now. Next thing we want to do is we switch from the engine is now set to band. That's our periodic DFT code, to ReXFF, which is what we'll be using throughout this tutorial. And the task that we want to perform is we want to perform a geometry optimization of this structure with including the lattice vectors. So full on geometry optimization. I select this as the task, and I'm going to select the force field parameters lithium sulfur.ff, which are the parameters that were especially made for this system. And these are also the parameters that were used in the publication that I showed on my first slide. We click on this arrow button here next to the task to go to the details panel for geometry optimizations and check the checkbox optimize lattice, because we want the lattice vectors to be optimized as well. And that was it. So now we can save. And I'm just going to call that solve for now. And then we can run the calculation. So we just go File, Run, or Control R is the keyboard shortcut. I'll probably be using that from now on as I'm so used to it. And it should only take, yes, the blink of an eye is already done. So the structure was already very good, or say very close to the predicted minimum structure of that force field we are using. Okay, so now I have an optimized bulk sulfur structure, and the reason why I did this is that I am interested in the total energy of this structure. Let me just go to this SCM menu over here and then output. And this is the output file of the calculation. And below here, you see a little magnifying glass. And in there, I will just type results. And then I can jump through the results here, through the findings of the search term. And I find the total energy in Hartree, so atomic units, as the first entry of the calculation results chapter. So minus 13.61, that corresponds to minus 8,550 kcal per mole, which is the unit given in the tutorial. I will skip the conversion for now, so you sort of have to trust me on this. If you're free to check if that conversion is correct, of course. So I note that very number because we're going to need it later on, and can move on now to calculating the energy of one lithium atom inside bulk lithium structure, which is what we need to retrieve our chemical potential of the lithium. So let's just start with a fresh input window. Switch to ReXFF again. Okay. Now I'm using the crystal building functionality. So I'm going to edit crystal, and I'm going to load a preset. So I'm going cubic BCC. And from there, I can select the lithium preset. So that gives me one lithium atom, but we do want to generate a supercell for this calculation. And this we can do by going to edit, crystal, generate supercell, and we're going for 8 by 8. And here you can see we have a block of bulk lithium. We pick the same force field as before, lithium sulfur.ff, and we also pick the same presets. So we want to run a geometry optimization, and we want the lattice to be optimized as well. And now we can save the calculation. That li. And then I'm using Control R to start the calculation. You can also go to File, Run. Oh, is that running now? Yes. Okay, so when I'm asked if I want to update the structure in AMP's input, I simply click yes. That means that the structure will be replaced with the one that we have just optimized. Again, we're going to open the output module and jump to the results section and then note the total energy. Results. There you go. So it's minus 30.7634 and so on. Again, total energy given in atomic units in Hartree. And that corresponds to minus 19,304 kcal per mole. That means if we just go back to the input window, click into this molecule panel over here and do Control A, we can see at the bottom a count of the atoms, 512 atoms. And what we're going to do now is we simply take the total energy that we have just taken out of the output file and divide it by the number of atoms inside our supercell, and this is our chemical potential of the lithium that we need to determine whether or not we have reached chemical equilibrium in the grand canonical Monte Carlo simulation. Okay, now with this calculations done, well, we can jump right into the question. Oh, I'm not changing the... So, okay, I'm going to just jump back to the input window in which I have optimized the sulfur structure. And I'm going to change the task now to GCMC, which stands for Grand Canonical Monte Carlo. If we click on the arrow button to the right here, we get to the details panel. And the ensemble that we want to simulate is constant chemical potential, pressure, and temperature. And by doing so, we allow the system to change its volume. So if we had gone for the ensemble with the constant volume, then we would obviously keep the volume fixed. And once we insert a lot of atoms into the system, we build up a lot of pressure. So if we keep the pressure constant, this means that the unit cell is allowed to shrink and expand, and we can observe volume change. We're going to go for 1,000 steps, 1,000 GCMC Monte Carlo iterations. And we are going to request that atoms are added within this system. So lithium atoms are added by the Monte Carlo algorithm within 6 angstrom, but not closer than 1.2 angstrom. And you might ask yourself, where do these numbers come from? To some extent, just from trial and error. So you see what works and what doesn't work. Obviously, if you allow the molecules not closer than and then a very small value, you want to prevent nuclear fusion happening. So if the Monte Carlo algorithm just naively places lithium ion exactly on top of a sulfur atom, you will have a near nuclear fusion, super high energy terms, and your whole simulation will just blow up. So you get all sorts of weird errors from that. But these are very solid, like very generally applicable GCMC parameters. Okay, so this is for the general setup of the Monte Carlo calculation, and now we obviously need to define which molecule should be inserted and what the chemical potential of this molecule is. For this, I click on the plus button next to molecules and select new molecule. And don't worry that the sulfur structure is vanished now. It's just opened another tab here in the molecular view panel. So the sulfur structure here is still there. Molecule 2 is going to be the particle that's about to be inserted. And that is going to be a lithium atom. Now the position of this lithium atom inside this unit cell does not matter for the calculation. I will just align it quick anyways. I'm going to edit crystal set 0.5, 0.5, 0.5, just so that it looks a bit nicer. And then we can insert the chemical potential that we have calculated earlier to be minus 37.7 kcal per mole. If you want to switch the unit, you can just click on the unit here and select a different unit, and that is true for every unit, or say almost every unit inside the graphical user interface. It might not look like this is possible, but it is. So that's an expert trick there. And with that done, we can save and start the calculation. I'm going to call that GCMC. Oh, the calculation was saved. And then I'm going to execute Control R, and that will start the calculation. With the running job selected, I can go to SCM AMS movie to follow the progress of the calculation in this little movie window. And you will see all sorts of atoms popping up, atoms, lithium ions moving around, being shifted. Also, you will see over time gradually the volume expanding of this cathode. The more lithiation takes place, the more the volume will expand. And this will now run for about an hour until it has reached, hopefully, the thermodynamic equilibrium. Keep in mind that this is not a molecular dynamics trajectory, so there is no time information here. These are just accepted Monte Carlo moves that we see here without any time information whatsoever. So I'm just going to close it for now and stop the calculation. You can keep your calculation running. And the post-processing step that I'm going to show you now on one of the calculations that I have prepared earlier, you can also carry out on your running calculation, but of course you will only get few data points then, but it should still work. All right. Now we scroll down. Maybe this is of interest here. So this is a small movie of the discharging process, and you can see the more the lithiation proceeds, the bigger the unit cell gets. Okay, in the tutorial, the voltage profile is calculated within the section analyzing the results. There's also a bit of science background behind this, so which approximations we make. Most namely is that we are dropping enthalpic and entropic contributions to work with the Gibbs free energies directly. And this was all already made by us and turned into a small Python script. And this is something that we often do because it gives us the possibility to create custom trajectory analysis tools. As you can imagine, this this sort of analysis of a Monte Carlo trajectory is not something that is a standard procedure. So that's very custom made. And for these custom made analysis approaches, Python is just the perfect language. And I'm not sure it was mentioned already. I guess so. My colleague Fedor mentioned it yesterday, but every AMS installation comes with a fully equipped scientific Python stack. So there's no need to install anything. Everything is already there. And this is what we're going to use now. We are just downloading the script. So again, the word that was said there was save link as, but in Dutch. And I'm just going to save this script inside the folder in which I ran the calculation. So as I said, this is an earlier calculation. So this is not the one that we had just started, but this one is already finished. And the script should lie in the same place as the .results directory. So the directory that contains the results from your calculations. So it's already downloaded once. I'm just going to replace it here. Okay, now the script is there. Now all we have to do is tell the script where to find the results that it should analyze. And for this, I'm going to open the AMS command line. And the AMS command line is available from help, from every GUI window, also from AMS input or from the movie. Help command line. On a Windows computer, on a Mac computer, it's called terminal, I believe, help terminal. And on a Linux machine, you are equipped with a first-class console anyway, so you can just open your standard preferred bash shell or whatever it is you like to use. Okay, on a Windows computer, I open the command line and I type in bash, because we not only ship a Python stack, but we also ship a minimal Linux-like bash console. Now let me just increase the font for you a little bit so that you can see what I am typing here. Okay, so the command line will open in the directory in which you last did a calculation, and we obviously just did this GCMC-2 calculation. Let me just change quickly into the directory in which I ran the previous calculation. Okay. Okay, to run the script, I'm typing in plums. That's the name of an interpreter. So I could also, for example, call a Python interpreter. That's called AMS Python. That's the Python interpreter shipped with AMS. But I am calling plums, which is the interpreter for our plums library. The plums library is a workflow library, and it's shipped also with the Amsterdam Modeling Suite and is extensively documented online. So plums, then the name of the script, lithium voltage profile, -v results dir, equals, and then the name of the directory with the results. And then I can hit enter. And while that program is working, I'm just going to show you where you can look that up. You will find this online in the tutorial as well. This is what I just did here. So now the Python script plows through all the Monte Carlo structures in the trajectory and calculates our voltage profiles as well as volume change. Gonna take a few seconds. and then the results will be printed to the command line. If you want, you can, of course, just redirect the output like you would normally do into a file. Again, this computer is not the most powerful machine. And there we go. So everything has been printed to the command line. I'm just going to copy that out of here, just for sake of simplicity now. Control C. And then I am opening whatever sort of plotting software we have available. And I just happen to have a spreadsheet calculator here. You can use, I don't know, QTI plot, Origin, GNU plot, whatever rings your bell. And there's a small formatting issues when importing it here. Let me just get this straight. And then we can have a look at it. Okay, so here we have now 4 columns of data. And what are these? You can see this in the header printed here. That's the number of lithium atoms, the fraction of lithium atoms. So that is the X in the lithium X sulfur. So this fraction as with regard to the sulfur atoms. Then we have the voltage in volts and the volume in cube angstrom. Let me just plot the voltage against the fraction of lithium atoms for now. Nothing fancy, just a standard plot. Just change the axis. So you can see a bit better what it looks like. And this is the voltage discharge curve of this battery. You can see, especially in the beginning, the data is kind of noisy, and that is simply because statistics are not so good yet. There's just a handful of lithium ions inserted into the system, and as we proceed, the simulation gets less noisy. So we have here the voltage and here the fraction of lithium ions. And a comparison with experimental data. I'm sorry, I only have the small sketch which I took from the paper. You can see here, let me just zoom in a bit, that this line here corresponds quite well with the experimental findings. So this line has not been shifted at all. This is just overlaying it. And what you also do see is, since this is a stochastic algorithm, stochastic sampling, that the outcome differs a bit every time you run it, but the overall trend should be the same, of course. Now, if we want to just have a look at, at the volume change, we can just do that the same way. Just to give you an idea, so you can see the volume expanding during discharge of the battery. And this is not the only insight you can get from these sort of calculations. In fact, you can get a lot more insight, as is demonstrated in the paper. So you can also calculate mechanical properties, for example, all sorts of materials properties. And what we want to do now is we do one more property, and that property is going to be the diffusion coefficients. Again, just to give you the idea, what we are going to do is we just pick one of the Monte Carlo generated structures. So you can see here, let me just do this full screen for now. It's just one slide. It might be a bit small. So it says lithium 0.4 sulfur. So that's just some intermediate. It's not yet fully discharged, but also not fully charged, you might say, somewhere in between. And from this structure, we are going to calculate our molecular dynamics trajectory, just like you would with all other molecular dynamics codes, except this time it's a reactive force field, of course, so the bonds between the sulfur and the lithium can be broken and formed again, and the ions are mobile inside the cathode, so they move around. And this mobility is, of course, what we are interested in. And what we are going to do to calculate the diffusion coefficients is we're going to use the velocity autocorrelation function. As shown here, we're going to integrate the velocity autocorrelation function. And for this approach, we need the trajectory to have a very high resolution. So we are going to record every 5th frame of the trajectory, which we're going to run at a temperature of 1600 K. And even with that high temperature, so high mobility, of course, and the high resolution, we still need an absolute minimum of 100,000 production steps molecular dynamics. We're going to equilibrate the thermostat for 10,000 steps, which is good practice, and then go for 100,000 steps production. It could or should be more for a production level quality. But since this is a tutorial, 100,000 already gives you a ballpark figure, gets you in the right order of magnitude for the diffusion coefficients. So once you have done that, you can repeat the process at different temperatures. And then you can use this data to extrapolate down to ambient temperatures. And this extrapolation scheme is necessary because you cannot just calculate the trajectory at 300 K, because there will be so little movement in the lithium ions that you would need to sample for an extremely unfeasibly long time of the trajectory. So it's better to just extrapolate using the Arrhenius equation, and that should give you an upper limit. So an upper bound to the diffusion coefficient at the ambient temperatures. So let's jump right into the tutorial. I'm going to close the input window from the Grand Canonical Monte Carlo simulation and open a fresh AMS input window. Again, I am clicking on Help and Tutorials. That will bring me to the offline documentation, molecular dynamics, and Monte Carlo. And at the end, you'll find, on the right side, at the end, you'll find lithium ion diffusion coefficients, which is what we would like to do now. We're going to jump right to the resulting lithium sulfur structure. This is the last line before the chapter importing the sulfur structure. Simply for matters of time, you can also construct this structure from scratch. This is explained here in the following few lines. We're just going to skip that one. Clicking on that structure, save a link as, and then just save it somewhere in our calculation folder. Of course, you can also just export one of your previously generated Monte Carlo snapshots and import this into our new AMS input window. File, import coordinates. Oh, where are we? Where did I save it? I have to look where I saved it. Okay. Okay. So there it is. Just going to open it, import it, and you can see here, this is this amorphous intermediate structure. And I'm just going to set up a simple molecular dynamics calculation now. We're going to use the same force field, lithium sulfur.ff. The task, molecular dynamics, and then jump to the details panel. Going 100,000 steps. A time step of 0.25 is actually okay. We have heavy atoms in the system. And then we change the sample frequency to 5. So that means that every 5 iterations, we are going to write out the coordinates of the system, so the atom positions as well as the velocities. The velocities is what we are interested in here. Then I'm going to follow the details to thermostat. Click on the plus button to activate a thermostat. We're going to go for the simple Berenson thermostat. This is not the best thermostat one can use, but it's a simple one that has also been used in the publication. We also have Nuss-Hoover chains, which produce much better ensembles. But for now, we're going to stick with the classic. Go for 1600 K and a damping constant of 100 femtoseconds. Pretty standard, everything, not much thought put into it. And then we can just save and run the calculation. Just call this diffusion. And I'm going to hit Control R and run the calculation. And you can see here the frame counter going up every 5 steps. We are writing a frame, so that's also going to produce a bit more data on your hard drive. Not crazy much though. Still a small system. And as opposed to the Monte Carlo simulation that we ran before, where there was no time, no concept of time, we have a concept of time now. So what you see here is the actual movement, or say a simulation of the movement of this lithium ions inside this sulfur cathode at a temperature of 1600 K. This will now run for, I think it depends a bit on your hardware, maybe 20 minutes roundabout, maybe less, maybe a bit more. But I shall just stop this for now and to jump to the ready-made trajectory. So job, I select the job, by the way. If I want to stop a job, I select it, job, kill. And then jump into the previous calculation I did. Look at where that one is. It should be this one. Yes. Okay, so I just opened the calculation in AMS Movie. Looks like this. And you can also see that it was a good idea to actually allow the thermostat to equilibrate for a couple of thousand steps as our total energy is adjusting to this, and we slowly converge and roughly stay constant. and so on and so forth. Very high frame rate, so a very, very unspectacular movie that just keeps going and going and going. But we did this so we can calculate the velocity autocorrelation function. So this time we don't need to call a script. Instead, we can just go to MD properties within AMPS movie and open a dialog for the autocorrelation function. Let's just call it lithium. You don't need to call it anything at all. And then request the trajectory to be analyzed, but not from step 1, but from step 2000, because that's when we have equilibrated our thermostat. And play a bit around with these values if you have finished your calculation, because in the velocity in the overview in the results panel for the velocity autocorrelation function, you can see how well the diffusion coefficients are converging and how well this integration converges also. And if you consider the non-equilibrated steps, you will see that the number gets notably off. The property that we want to calculate an autocorrelation function from is, of course, velocities, as I said. Now we need to say for which atoms this should be done. So I'm just going to go into this molecular view panel and select one of the lithium atoms. Then I go to select and select atoms of same type. So selecting all lithium atoms. Then bring the autocorrelation function dialog back up and just click on the plus button right next to the atoms. And now I can just click on Generate ACF to start the calculation of the diffusion coefficients. See a nice progress bar that you don't get, of course, if you run something from the command line, unless you put that into your script. And there you go. This is the overview of the results. So the actual diffusion coefficient is given here. 3.2 times 10 to the power of -8 square meters per second. And stats for the calculation of the auto velocity of the autocorrelation function are given in the above windows. The interesting bit that I usually look at is the convergence of the actual quantity. So in this case, the lithium diffusion coefficient, you can zoom in and you can see, okay, it's still somewhat fluctuating, but you get an idea that the order of magnitude at least might be somewhat converged. The longer you run the trajectory, the better this will get, obviously. And yeah, the more movement there is by the lithium ions, the better it will be as well. So if there's hardly any movement at all, there's hardly anything to sample at this low temperatures, and then we'll get a very crude, I'll say even bluntly wrong estimate of the diffusion coefficient. And that would be our first value also for the Arrhenius plot, from which we can then extrapolate down to ambient temperatures. How this is done is explained also at the end of the tutorial. And with this, I have finished my demonstration, my little overview on battery modeling workflows, on a selection of these two battery modeling workflows, and I'm happy to answer any questions.
So thank you, Ole, for your wonderful session.
You're welcome.
So I'm sure that participants will have queries. So I request everyone to unmute yourself one by one if you have any questions.
Hello. Good evening, sir. I am
Hello.
Vaibhav. Am I audible?
Yes.
Okay. So, am I talking to Wally, sir?
Yes, you do.
Oh, yeah. Okay. So I just wanted to ask that when we were calculating the chemical potential for lithium, we
Yes.
took a specific supercell that is 8 into 8 into 8. So if
Yes.
I take a different dimension, then would how would it result in the change?
So
How will the
that
results change? Yeah.
the results will not change significantly. The reason why we are doing this is actually, yeah, it might be a by now almost deprecated technical reason. So the reactive force field has a charge equilibration scheme because if bonds are broken and formed, you need to equilibrate charges at some point. And the charge equilibration scheme could not handle unit cells that were below, I think the threshold was 10, 15 angstrom per dimension. So I say it could handle it, but there was the risk of it going sideways. So the safe bet was always to say, okay, better take a bigger unit cell because the charge equilibration scheme is just handling it better. So, but if you do use a bigger supercell, you just divide by a bigger number of atoms, you should end up on the same chemical potential.
Yes, sir. Yes. Got it, sir. Thank you.
You're welcome.
Is there any other questions?
Yes, ma'am. Yes, ma'am. Ma'am, I'm audible. Hello.
Yeah, please go ahead.
Yeah. So, good evening, sir.
Hello.
Hello, sir. Myself, Durga Prasad. I got a small doubt over the software. What kind of extensions the software can handle with file type?
Sorry, can you say again, please? That was cut off.
No. What kind of file extensions the software can deal with?
Pretty much all standard extensions. So you mean importing, exporting. So what I used now here was a crystallography file, so a CIF file. You can import PDB, XYZ, basically pretty much everything, even smiles. You can smile strings, chemical identifiers you can import.
Yes, sir. Thank you.
Hello.
Hello.
Hello, sir. There is two questions from my side. One is the what will be the script for the other system if we don't have lithium sulfur system? And other question is you said that you have to equilibrate the system for some steps. So how we give input for this equilibration in the reaction of input?
I'm sorry. Can you? I'm not sure I understood. So the one question was that what needs to be changed if something other than lithium ions are inserted into or used as charge carriers. Is that correct?
Yes, sir. Yes, sir.
Okay.
Like you downloaded from the tutorial for the extension like Python script. So what will be the script if we use different system?
Well, just have a look at what the script says. So you will obviously what the script basically does. It's counting atoms. So what you will need to tell the script that it should not look for lithium atoms, but it should look for here it is. Am I still sharing my screen?
Yes, sir.
Okay. So yeah, so basically this is the line here. I mean, you're counting the charge carriers for your system. So you need to count something else, and here it is. Yeah, the number of lithium atoms summed over all atom symbols that equals lithium. So then you need to change that according to some other atom.
Okay, thank you, sir. My second question is, sir, you said about you have to evaluate the system for few steps before the production run. So how to
Yes.
give this input in ReactSFF? That like you did not show the where to give this equilibration step in the input of ReactSFF.
Dr. Ole,
So
can you
yeah.
please share your screen? It's not
So
visible.
okay, I see. I'm sorry. Let me just screen one. So now you should see it. So this is the line in the script that you want to adjust. So this
Yes,
is
sir.
what I meant with we are counting the lithium ions, and then if you have something else you want to count, yeah, some other species there. And sorry, the second question was?
Second question is to how to give the equilibration step before the production run in the ReactSFF input.
Okay, so in the you mean in the calculation of the diffusion coefficients, or when we optimize the geometry?
Oh, sir, during the calculation of diffusion.
Yeah, yeah. Okay, that choosing the number of steps is indeed something that you might not know beforehand. So it's not that I can just look at a structure and say, okay, this one's going to take 7,899 steps of equilibration. Instead, what I suggest one should do is you start the calculation and then you look at the temperature or the energy as a first hint. You know, the energy I've shown in the AMS movie window. But the most direct measure would obviously be the temperature itself. And if you see that jumping around like crazy, then it's not equilibrated. If you see this not converging to a certain value, then after, I don't know, say 10,000, 20,000 steps, then it could also be that you just need to change the settings of the thermostat and the barostat. And for this, let me just real quick, you still see my screen, right?
Yes, sir.
Okay, so if you just go to our website, we have an FAQ, so frequently asked questions, under the support on top. Just click on that one, go to ReactSFF, and at the end, we have practical advice here on choosing proper realistic thermostats and barostats for your simulations. So how long does it take to equilibrate depending on different systems? What thermostats and barostats are there? What damping constants should I choose, and so on and so forth. Some pitfalls like the flying ice cube problem. This is a really good read, and that should definitely get you started on that matter.
Okay, sure, sir. I will go through it.
Excuse me, sir.
Hello.
Hello.
Hello. I can hear you.
Yes. Okay. Sir, I wanted to ask that what is the basis of accepting a move or rejecting a move by GCMC? Is it solely based on the energy, that if the energy of the system is decreasing, then it will accept?
Yes. So if the energy decreases, yeah, in fact it's a bit more complicated, but you can find, because there's also a prefactor that is calculated. If you click, if you have the slides, I'm not sure if you already have them. Otherwise, you find it in the documentation as well. We have a whole chapter on the Grand Canonical Monte Carlo. And how it works is in detail explained here. So what basically happens is that you will always accept a move that is favorable in terms of energy, if I remember correctly. And if the move is not favorable, you will accept with decaying probability the more unfavorable it is. So yeah, standard Monte Carlo procedure.
Okay.
And
Definitely,
yeah.
sir.
And you can find all the details also with respect to other grand canonical Monte Carlo simulations. You can also have gas phase reservoir calculations and so on and so forth, detailed here in this chapter. How the volumes are calculated is also not immediately obvious, but is documented quite well. And if you're missing something, you can always reach out to us on support and ask for clarification.
Sure. Thanks a lot, sir.
You're welcome.
So is there any other questions? Fine. So due to interest of time, we will be rest of the questions will be taken via Discord. Dr. Ole, you can stop sharing your screen.
All right. Let me see how I can do that.
Yeah, thank you so much.
Okay, thank you.
So there are instructions have been emailed yesterday. Those are software download links, download credentials, workshop materials, and other tutorials and video presentations links also have been emailed. So I request everyone to check your spam or junk folder. So if you have any queries, you can always reach us at scm@nyroindia.org. So it's time to conclude the session. So today we are ending up the session. We will meet again on the same platform tomorrow at 4 p.m. So stay safe. Thank you all.